Welcome to our inaugural session of the Innovation in Infrastructure podcast series, brought to you by Roland Berger's regulated and infrastructure platform. My name is Yvonne. I'm your host for today, and today we will be diving deep into the world of carbon capture, storage and utilization, or CCUS for short. I'm here with my senior partner colleague, David Frans, who's one of the driving forces behind our CCUS team. Welcome to the show, David.
Thank you, Yvonne. Great to be here today.
So let's kick things off. You and I go years back when we started rolling out our Sustainability Climate Action Center of Excellence. And I know you're really passionate about climate change. And I know you also think CCUS plays a huge role about it. So now for our more listeners who are new into the topic, could you please explain what this actually is and why it's so important for climate action?
Thank you, Yvonne. I'll start with kind of sketching the bigger picture, because everyone knows we have a global climate change problem. The globe is warming. And that's because we have greenhouse gas emissions, which we emit freely, and we've been doing now for quite a few decades. Every year we emit roughly 55 gigatons, and that needs to go to zero. That's a very big challenge. So for that, there are numerous ways. Think renewable electricity that doesn't combust fossil fuels. Think things like green or blue hydrogen, but also capturing carbon, just preventing it from getting into the atmosphere, or actually taking it out of the atmosphere and putting it back into the ground. That is, in short, carbon capture.
That's fascinating. And what are the current trends and developments we see in the space of CCUS? Where does it stand? What role can it play?
Let's start with your second question, what role it can play. And I'd actually like to phrase it slightly differently. It's about what role should it play. I want to put the numbers into perspective. We at the moment have 55 gigatons of emissions every year, give or take a few gigatons. We need to be by zero by 2050, and in 2030 we need to already have roughly 26 gigatons left, or less than we have now. That's just 7 years. So what can you do to bring that down? Well, people know the big things, such as switching cars to battery electric vehicles. Now, let's just imagine if all cars on the road in 2030 would be battery electric vehicle, that would reduce global emissions by roughly 3 gigatons, nowhere close to the 26 that we need to be. Or people then talk about, well, why don't we switch aviation or maritime to synthetic aviation fuels or sustainable aviation fuels? Well, if you do that for both marine and aviation, that saves us roughly 2 gigatons. But remember, we need to have already 26 gigatons less by 2030. There are other big levers such as renewable electricity. Think solar, onshore wind, offshore wind, hydropower. But also those are still, so there are several gigatons, 10, 15, depends a bit on the assumptions you make. But together, all of those things that politicians are seeing to have being realized by 2050 would already have to take place by 2030, and we're not even close. So we need solutions that offer gigaton scale carbon capture. So that's where it comes in.
Yes, so it's clear we cannot reach our climate targets without carbon capture, storage and utilization. It is part of the decarbonization story that our world has to live with. And also the Intergovernmental Panel on Climate Change sees a huge role in it in all net zero scenarios. But we also know that countries look at its role a bit differently. So what do you see? What are governments doing to use and really leverage the potential that we have here?
I'll give you 3 examples from more or less the 3 biggest economies in the world. There's the United States, there's Europe, there's China. And all 3 are actually taking a different path here. The United States has the so-called Inflation Reduction Act. I think many of the listeners will be familiar with that. There's one section in it which actually gives a subsidy of around $85 for every ton of CO2 that is captured and stored. That actually makes it interesting. European Union has a different scheme. There's the ETS, which puts a cap to the amount of carbon that we can emit. Then there's a trading scheme. So it's more like, works like a tax. And at the moment, that tax is quite expensive. We're already talking 90 euros. The forecasts are that that will go up to 100, 150, 200. That's also where it needs to be. Otherwise, you're not going to make a switch. Because eventually, It's all about economics. China is now looking at things such as introducing a similar cap and trade scheme, but they're actually already making quite a few projects. So they've invested in energy, electricity creation, but then coupled with carbon capture and storage. They're doing that, for instance, offshore. So these things are starting to happen. The most important for governments is that you actually put a price to emitting carbon. Why do we emit so much carbon? 55 gigatons is really a lot of carbon because it's for free. And we love things that are for free. So as long as it doesn't cost us any money to emit CO2, we'll keep doing that. Hence, a tax or a subsidy then to capture is a policy measure that you need for this to really start working.
Absolutely. And you've spoken about the economics already. So I think its role and potential is clear. Now, when we talk about decarbonization and climate action, it's always clear that there are so-called hard-to-abate industries, base materials like steel, like cement, like others, that are not so easy comparatively or relatively to decarbonize. What role can CCUS play to help those industries decarbonize? And what challenges do you see for companies to really make use of this technology?
Let's take 3 different examples of industries. One is the steel industry, the other is, for instance, cement, and the third is chemical. These are 3 big industries. Everyone can envision a large factory. These are very big factories typically. And you can have emissions ranging between 500,000 tons from one of these sites to several million tons if we're talking about the biggest factories. But all 3 of them have actually different ways why they emit CO2. In the chemical industry, you emit CO2 because you typically want high temperature heat, for instance, in the form of steam or in the form of a furnace. So for that, you combust natural gas. And in some regions of the world, we're still combusting a lot of coal. With cement, we have also the need for high temperature heat, but the process of cement making itself also emits CO2. So the calcination of cement, that process itself results in CO2 emissions. And that is not something that you can change. Even if you create that high temperature heat with electricity, which is renewable, you'll still have those process emissions. In the steel industry, it's a bit similar. There we use, for instance, coal or natural gas as a reducing agent. It is iron ore. You need to take out the oxygen so it binds with the carbon, and then you emit CO2. So all 3 have CO2 emissions. The good news for the steel sector is there are also alternative ways of direct reduced iron. For instance, using hydrogen. Then you don't have any CO2 emissions. And if you look at actually how much CO2 do you avoid by using hydrogen, the effect in the steel industry is actually the biggest. And as hydrogen will be in short supply for many years, maybe even decades, you want to put that hydrogen to use there where it has the biggest effect. The steel industry is a good example. But for instance, for the cement industry, that doesn't work. So you'll need to then capture that CO2. You could also capture the CO2 actually for some steel industries. It doesn't have to be purely based on hydrogen. You capture it there. And in the chemical industry, where you need high temperature heat like steam, it's also one of the means to capture that CO2, eventually either utilize it or put it in the ground so that we prevent it coming into our atmosphere. Because that's what we need to do. We need to make sure it doesn't come into the atmosphere. You already alluded to the IPCC about we will need carbon capture. That's also because we need to get to something called net zero. Everyone recognizes that some emissions will remain. So we'll need to compensate for those remaining emissions. That means you need to have negative emissions somewhere else. You can do that, for instance, by taking CO2 out of the atmosphere, think direct air capture, or by combusting something which has a biogenic source, then capturing that CO2 and putting that into the ground.
That all sounds so convincing and so straightforward, especially because it seems like the technology has been proven for industries. It's available. So why, going back to the economics, why don't companies just roll it out today? What is standing in our way?
Well, the economics differ per industry, but just to give you a rough number, carbon capture and storage costs roughly €100 per ton. Up to 150, depends a bit on the industry. So only there where the cost of emitting comes close to that number. Is it economic? And at the moment, that's only in Europe. In the United States, there's no carbon tax, but there is now a subsidy. So if you capture it, if you emit now, it's for free. If you capture it and your cost is roughly $100 per ton, you can get an $85 per ton subsidy. And then it becomes economic because some of the customers of products that are made that emit CO2 might be willing to pay a small premium. So that would then cover that $15 delta. But as long as there's no subsidy or no tax, nothing will happen.
And that's where we're back at the point initially where we know governments need to create the framework conditions for investment to happen into this sector.
Absolutely. Governmental action here is crucial. Without either a subsidy, a tax, the government forbidding something or obliging something, nothing will happen. Yes, things will happen on smaller scale because there are always a number of companies, a number of individuals, wealthy individuals that want to do things for the greater good. But on a scale of billions of people, it all boils down to economics. Things need to make economic sense. And at the moment, without a tax or without a subsidy, it doesn't make sense because it just costs money. And we should not forget, energy is extremely cheap. People in Europe might not see that at the moment because we've just gone through quite an energy crisis, but still, energy is very cheap. There are not many businesses where the cost of energy goes above single-digit percentage in their total cost. Why is it cheap? Because we haven't taken into account, for instance, these externalities, such as the cost of emitting CO2.
Now, for those listeners who are focusing or hearing about carbon capture, utilization and storage for the first time, there might be a concern about what do you actually do with that captured carbon? Storage, is it safe? Will it not emit back into the atmosphere? What do you say to those groups of listeners?
It's a good question. I'd say if you don't capture, you're emitting 100% of CO2 into the atmosphere. And we all accept that as safe. Now, if instead of emitting 100% into the atmosphere, we can capture 95% and we can store it, and there's decades of knowledge about storing gases underground. We're storing lots of methane underground. Methane comes from underground. We take it out, but we also store it underground. So we know very well how to deal with these geological sites. Yes, there could be leakage. There's some studies about between, let's say, 0.1 and maybe 1%. But even, let's just imagine that it would be 1%. Is that a bad thing? Because now we're emitting 100%. If you'd capture it, store it, and you only emit 100%, we've had 99% less. So that's a good thing. Because we need to go from 55 gigatons per year now to about 30 in 2030. So that's already minus 25, and we need to get to zero. And we're not on that trajectory. So we need these gigaton scale solutions.
All clear in terms of the mathematics, understood. Now, wouldn't you see that there is a danger of some companies or countries using carbon capture and storage and utilization as an excuse not to invest into actual CO2 mitigation from the outset? So investing in renewable energies, in cleaner technologies. You've mentioned alternatives in steel production, for example, DRI, in producing green hydrogen and using that. Wouldn't the focus or the reliance on CCUS prevent that push to actually go for some other technologies which add to the net zero scenario that we also need to the net zero scenario?
No, I don't think that's the case, Yvonne. We're here at a global scale and we need to do things efficiently. So you need to have many different routes to reduce emissions. And you mentioned several of them: green hydrogen, renewables, efficiency, etc. All of these things need to take place. The nice thing about businesses is they do first what is most economical. And for instance, reducing energy usage prevents CO2 emissions is typically the thing you do first. And there's actually a lot to be won there. Typical businesses that we work with can reduce their emissions or their energy usage and hence their emissions by 10 to 20% relatively easily without actually costing money. So if you then look at what's the cost per ton of CO2 avoided, it's actually negative. That's great. Using renewables, in many cases, for electricity generation also has a negative cost per ton of CO2 avoided. Other things such as hydrogen, they don't, because there's quite a lot of technology that goes with it. Electrolysis is actually very difficult, but it's one of those pathways to get there. Carbon capture and storage is another. What we see is we need to bring down those emissions. We could do that by just using far less energy, but that's not what we want. If we look at the COVID years, when more than half of the global population was in a lockdown, that's a very, very severe situation. That year, we had roughly -7% emissions. The year after, it should have been again -7, and this year again, and next year again, to be on that trajectory to net zero. So we're not there. And it shows just how difficult it is to reduce by 6-7% per year. You need to lock down half of the world. Now, that's not what we want to do. We want to keep living the way we do. We're going to have another billion people starting to use more energy than they've been doing over the last years, rightfully so. So energy demand is still forecasted to go up. That's because some of the wealthier countries, now energy demand is going down because of these energy efficiency measures, but on a global scale, energy demand will still go up. And we just cannot meet that yet with purely renewables. We need to increase the deployment of renewables by a factor of 4 globally. That is possible. I'm 100% convinced. But it's going to take still quite a few years. So we need, in that intermediate period, and the intermediate period is unfortunately decades, we need gigaton scale solutions. Carbon capture and storage is one of those.
Mm-hmm. Yeah, thank you. Very, very clear and fascinating. You've been referring to other clean tech, to other energy carriers like hydrogen and electrolysis that enables the production of green hydrogen. We will have another session dedicated on hydrogen at some point, so that will come up again. But maybe you can already talk a bit more about how CCUS actually links and leverages other clean tech or technologies and energy carriers, and what are the connections that you see, what it's needed for additionally.
One of the crucial things that you need for this to be a success is you need to bring together many stakeholders and you need to develop infrastructure. And everyone knows power lines because we typically see them, especially if you're outside of cities. People are less familiar with all the gas networks that are typically below ground, but they're there and they've been built and they allow every big user, small user, be it a household or be it an industry, to be connected. If you think about getting hydrogen to where we need it, or getting CO2 from a large point source emitter to somewhere where you store it, you also need infrastructure. And you're not going to build that infrastructure for just one small party. Then the economics don't work. So you need to look at industrial clusters. Where do you have multiple large emitters so that together they emit several million tons of CO2? Then it makes sense to actually put a pipeline into the ground, make sure you can actually export that CO2 to somewhere where you can store. That can be onshore, or as we now see in Europe, for instance, in Norway, in the UK, in Denmark, they're developing, in the Netherlands, they're developing several offshore storage sites.
Mm-hmm. Now, we haven't spoken about one element in this CCUS abbreviation, specifically about the U, the utilization of it. Wouldn't it be so great if we could capture the carbon and use it directly in another fuel or other product? How are the prospects of that actually balancing out?
Very good question. And I sometimes talk about the false promise of utilization. It sounds super nice. Let's just reuse that CO2. Here there's a problem of scale. One of our clients once asked us, well, can't we use that CO2 for carbonated water? We all drink it. We all love our fizzy drinks. That's because there's CO2 in it. Well, we did the mathematics. For that one site that they had, the emissions that come from that one site would be enough to produce more than the global demand of carbonated water. So you see, that doesn't work. Then people talk about, well, why don't we use it, for instance, to cure concrete? That's one of the ways. But also there, the amount of concrete that you would need vastly outnumbers the amount of concrete that we produce every year. So also that doesn't work. There's one area where it could work, and that is in e-fuels or synthetic fuels, because you need a lot of CO2 to create synthetic fuels. You also can see it the other way around. Burning fuels creates a lot of CO2. And from a mass balance perspective, you need to put in a lot of CO2 to get those carbon atoms into a synthetic fuel. But there, we also get a problem of logistics, because a very large emitting plant will create lots of synthetic fuel. We did this for a big cement player, and then the question is, will they then become a cement player or a synthetic fuel player? Because if you look at the value chain around those synthetic fuels, that's actually worth much more than the entire cement that they're creating. So that brings other problems with it. And then I'm not even talking about the logistical problems with a cement plant typically not being located next to an airport where they need those synthetic fuels. So there's a very, very big challenge. You can also look at it from another perspective, those synthetic fuels and CO2, what's the cost per ton of CO2 avoided? Well, maybe it's then actually cheaper just to capture that CO2, put it into the ground. Then you've also avoided, or you actually have a negative CO2 emission.
Yes, I think the good news in that context is there has been a quota that's introduced in the EU for synthetic fuels of 1.2% until 2030 for power-to-liquid synthetic fuels in a total quota of 6% sustainable aviation fuel. So a market will develop for this overnight, you could say. So there's a certain volume that will be produced and utilized. But of course, I think bottom line of your answer is we will not be able to get into the full utilization. We will also need storage in the end of the day.
Yes, and just thinking about this example of these quota that the EU has, the important thing there is that the CO2 used for those synthetic fuels actually has a biogenic origin. Because if that comes from combusting a fossil fuel or from like methane, then what you're doing is you're only deferring, let's say, the emissions into the atmosphere by, let it be 2 weeks or 2 months. Of course, from an energy perspective, you have less CO2 per energy delivered to the world, because you first deliver energy in the form of, let's say, electricity, and then energy in the form of an aviation fuel, but you're still emitting CO2. Whereas if the CO2 is a biogenic source, and that's why the legislation also actually counts for that. So depending on the source, you only have until 2035 or 2040, and after that, it has to be biogenic source.
Absolutely. So carbon doesn't equal carbon. There's different sources and different ways how they can be utilized to help the climate to get to net zero.
Indeed.
So Roland Berger has always been at the forefront of innovation and clean tech. How is our firm positioning regarding CCUS?
Well, we work with all players along the value chain. It starts with those that emit a lot of CO2. Then there's technology companies that capture the CO2. Then comes the part of all the infrastructure required. So there's companies that transport CO2 either via pipelines, through harbors or ships, and the governments that are putting the policy in place. And what really excites me about this is we're looking at a market potential of, think about $1 trillion per year. If you have 10 gigatons of CCS per annum at more or less a rough cost of $100 per ton, that's $1 trillion market. And when we work with clients, we show them that potential, we show them the difficulties, and we work with them to bring all stakeholders together. Those are the things that also excite me.
Fantastic. This has been very inspiring and enlightening, David. Thank you very much for joining us and for sharing insights on CCUS in this podcast today. Thank you very much, everyone, for tuning into this episode of Innovation in Infrastructure today. Stay tuned for more episodes and more topics around innovation in infrastructure, clean tech, and how to combat climate change. We look forward to connecting again.